Yeah, g'day guys, just Ben here. Just today we're just going to talk, or in this session we're just going to talk about reliability in our data and how we can apply that to sample collection. I guess the very first thing we want to talk about is what does the term reliability mean? And sometimes we talk about reliability as in very loose terms, but realistically, I mean, the Oxford Dictionary meaning of it is the act of being consistently good or in quality or performance, and realistically, that translates to being able to be trusted. In scientific terms, reliability is actually used to describe the chance of our sample set or what we take. It could be a set of biological samples, it could be a set of routine measurements, and those samples or measurements representing the total population of what we're actually trying to achieve, particularly when we're talking about sampling for animals. We might be testing for water quality samples, and in that situation, it will be the sample set representing the total water quality parameters of that biological or that ecosystem at that point in time, I guess might be the easiest way to describe it. All right, so why do we need it? And the simple fact is, without it, we, even as human beings, I guess we can say, is that our natural inclination is to bias things without even really knowing it. So having an opinion on something forces us or even encourages us to bias our opinion or our statement, if you want to think about it that way, purely from what we've heard or what we already perceive. And a bias, for those who don't know, is an inclination or a prejudice for one against for or against one person or group, especially in a way of considering things to be unfair. That's a bit of a definition, but I might just use the example if we used population statistics of the population of China to estimate the impact of the human race on the planet. Now, that would simply be a biased situation where we would be looking at A, there's a cultural difference, B, their heavy population is not a correct measure of what the population density is on the planet, and there's heaps of other factors that would bias our results, and we may end up in a situation where our result may encourage us to make a really bad decision or a bad batch of decisions we might consider. So, for us to be unbiased is a really good way of being able to, or trying to achieve unbiased results, I guess is a way of explaining it, is a way of us trying to get the most natural figures from our environment or from our fishery or whatever we're looking at. So to perform reliable collection, what do we need to do? Now, it depends on what type of program we're going to look at, but in general terms, we need to look at what we want to achieve. And that's not always very easy, particularly for people at lower levels in departments, and they may be associated with programs that they don't really totally understand 100%. Hence why we're trying to give you a bit of a snapshot, I guess, in this presentation as to how and why and when and things get given to you as to why they're being done that way. They might not necessarily seem, what's the word for it, necessarily be easy to understand, because science sometimes isn't directly linked to logic, I guess is the way I'm trying to describe it. So realistically, we need to know what our outcome is at the other end. So do we just want some pictures to be able to put up and show to people, this is where fish move from point A to point B, this is how fast they grew in that area, this is the length weight measurements for these fish for this year, just to paint a picture? And the reality is that has some weak power attached to it. We don't have a lot of assumptive power around that. We don't have a lot of statistical power around that. It more just paints a bit of a background picture, and sometimes those descriptive statistics, we call them, are the precursor to more in-depth statistical modelling and so on and so forth, to be able to make inferences about a population or a particular ecosystem or whatever we're looking at. So, in saying that, do we want to look at using powerful statistics to validate assumptions? And sometimes we say never assume anything, and that basically means don't go out there and say, oh, I was assuming that the weather was going to be great, or I was assuming that the fish would eat this bait, or I was assuming that you picked up the ice. They're the sort of assumptions we don't want to use in our science or data collection, so on and so forth. but we can make other assumptions that are more statistical related, and we talk about them a bit down the track. And normally related to this statistical inferential assumptions where we're making inferences about a particular product out of a fishery, for instance, they need to have strong power, and if they don't have strong sampling power attached to them, they become unreliable, I guess is the easiest term to say that. So to do that, the science guys at the top end of the hierarchy would be looking to perform power analysis, and that really says that if I take a small sample out of a population that we don't have a strong understanding of, say there's 1 million fish out there, we can't be sure whether it's 1 million fish or 2 million fish or 500,000 fish or whatever it is, we need to sort of make a bit of an inference about that and then run a sample power test to see, can I collect 10 fish to do that with a heavy amount of power, or so on and so forth. And typically the more samples we take out of a population, generally speaking, the higher the power gets. So the more strong the power is, the more reliable our data becomes. Right, and just want to make a note here that this stuff, I'm not anticipating that you guys will be doing any of this stuff. I'm not going to encourage you to do any heavy statistics or anything like that. I just need you to be aware that this stuff is there in the background. So if you do get to the situation where you become a person that's a field officer or whatever it might be, or you be part of a project where you need to go out and conduct sample collections, that you can sort of have a bit of a background knowledge about why scientists talk the way they do, I guess. And a really important part of the process for those scientists is to try and convert their programs over in a strategic planning phase, I guess, to the research team, so that the research team understands that if I make a mistake here, this is what it translates to down the line. And hopefully out of that, you guys would then seek to identify how that sample design might roll out to limit the bias, and that may mean randomizing sample sets via, the use of quadrats, transects, where we run down a line and randomly allocate length measurements along that line to sort of sample for things like, crabs and mussels and oysters and things like that. I won't go into too much detail, but realistically, when we're seeking to do sampling design, the only way to limit bias, or one of the best ways to limit bias, is to randomise it. That might be a random number generator, it might be any number of ways to randomise the design. But once again, that comes back to the scientists at the top level, and they really should knock that stuff down and nail it out in a strategic planning phase. And that really brings us down to establishing how it's going to be sampled, how the data is going to be collected, the recording and equipment requirements, and any potential analysis templates. So in this phase, we really want to be thinking about how to speed up the process, how to make it as robust as possible while minimising mistakes, and also thinking ahead of the game. If we look at a population, we'll talk about it in a minute through this presentation, about things that we may need to transform before we apply any statistical techniques. And realistically, I think that's our next couple of slides. So when we're talking about experimental tests, this stuff comes out, and normally it's a bunch of number crunching. It's done by those scientists I keep talking about, and they will make the assumption as to whether it's going to be a parametric or a non-parametric test. And basically a parametric test is usually a powerful statistical tool, but it relies heavily on assumptions about a population, and it assumes, generally speaking, that we have an idea about how the population is distributed. And I don't mean that it's distributed east to west or north to south or top to bottom or left to right. I mean how the parameters that we're looking at, and for instance, the most used one that we probably would see a lot of is the normal distribution, which we have here. On the right hand side there, we've got a normal distribution for, it's actually a school score, but if we use that in say length measurement for barramundi, for instance, if we work from left to right, we would start off with roughly 3 fish at a 60 centimetre mark, like 10 fish at 65 centimetres, 12 fish at 70 centimetres, so on and so forth, in 5 centimetre increments. And you can see that it's a nice neat shape, and the line that's overlaid it is what we call a bell curve. And the average in that situation, if we just take we add 60 to 100 down the bottom here, down here, 60% to 100% or 60 centimetres to 100 centimetres. We divide that by 2 because it's 2 counts. We should get a measurement of 80, which is our mean up here. So in this population, we made 100 measurements and the mean was 80 centimetres. Let's just say that for example. Realistically, if we think about it just as a schematic, I guess, the median or the mode or the mean, whichever one we talk, is about roughly the middle point depending on what we want to calculate. And generally we talk about the mean being the average. All right, either side of that average, we should roughly have 50% distributed either side of the mean in terms of numbers. To give us our uniform bell curve, I guess, is the most nicest way to put it. And in that situation, if we've got a population that looks like that, it's quite easy for us to run a parametric test and get some really solid, powerful data out of it. If we don't, and we end up with the need to run a non-parametric test, the testing itself isn't really as robust and isn't as reliable. But it's most commonly used where there's doubt about the distribution of the test parameters itself. So if we don't know whether it's normal or not in that situation that we've got here, they're all somewhat normal. They kind of look a bit like it, but they're really not. So in this situation where we've got we're measuring weight here by the number of individuals, we can see that we've got this bimodal relationship. And this generally operates where we've got mixed species, so we might be looking at 2 different species on this chart. We don't really know what they are at this point because I don't know where the data came from. So we might have flathead and pink snapper, for instance, and we're just looking at those numbers just as they are to see what the individuals look like. We might be looking at 2 different year classes of fish. This might be year 1 and this might be year 2 of the same species. We could be looking at males in a population and females in a population, where we know the males are bigger and the females are smaller. Over here we've got what's called a positive and a negative skew on our chart, or sometimes it's called skewed to the left and skewed to the right. In this situation we would indicate that we would have, if we were thinking about say barramundi again, because it's quite easy to think about where the big part of the population of fish that we're talking about is female and the small part is male, we could be making the assumption that roughly fish over a metre in length are all female, and we could be thinking that the higher proportion in this population is female and that we're an ageing population with not a lot of recruitment below that because there's not a lot of small juveniles in the population. Consequently, we can go the other way where we have a lot of juveniles in our population and not a lot of females or not a lot of ageing fish in our stock. This could be a good thing for a year where we've had, just this last year for us at the aquaculture centre here, we've had a lot of rain in Broome. And we know that the local waterways have a lot of juveniles in at the moment. If we went out and surveyed at the moment, we would find that we may have a skewed population in to the right at the moment, because there's a comparative abundance of small fish in the population rather than big fish. Consequently, that's not what this chart's about here. We're talking about egg to smolt survival in Atlantic salmon. But it's just an example of what these charts look like. Now, in this situation, we can already perceive that this may be the population that we want to work with. It might be a historical thing, it might be a research thing that the researchers have gone and done, and they may have already planned to do things like take our data and then transform it, whether it's a log transform, there may be a square root transform, where we try to make sure that it's kind of like straightening out a line, I guess it's probably the easiest way to describe it. Rather than having a bent line, we might try and straighten it out, because a straight line is going to give us the ability to compare apples with apples rather than oranges with apples. I guess that's the easiest way to try and describe it. But like I say, I'm not going to get you guys to do too much of this stuff unless we find the need or someone really wants to down the line. And typically one of the easiest ways to do that is to do a length weight measurement on a particular species of fish. We do a log transform on the data for the length and the weight. We combine them and then we run a model off it to say, hey, at 10 centimetres this fish equals this length, so on and so forth. We do regression analysis with that, providing that we've got an assumption already that the population is normally distributed. Okay, so moving on. Parametric tests include an analysis of variance, or what we call an ANOVA, regression analysis, t-tests, and cluster analysis. Now, I'm not going to show you what these are because I don't really think that I will have enough time in this presentation without boring the crap out of you. But if you go off and have a look at, just type in analysis of variance or ANOVA into a search engine, probably Google Scholar or something, and just have a look at what an analysis of variance does. Likewise for regression, t-test, cluster analysis. And realistically with those, it means that we can compare apples with apples to get a length measurement, maybe weighed up against an age measurement, for instance, and compare them over time. We may compare different populations within that measurement of length versus age, whatever it might be. The alternative non-parametric tests include a Kruskal-Wallis test, Spearman's correlation rank, and a Manley-Whitney U test. I always get that one a bit mumbled up. And they really don't have the power that parametric tests have. But once again, if we don't have the time, we don't have the foresight to understand what the distribution is like in the population, we may revert to saying, hey, if we don't get a normal distribution, we can't transform it for whatever reason it might be, we might just revert to these non-parametric tests to get a result. Okay, so if there is ever any doubt about the distribution within the samples or whatever we're testing for, then it's better to use a non-parametric test for alternative analysis so that we don't get caught up in getting hammered by some science Nazi down the line and saying that your results are all biased or they're unreliable or whatever we want to talk about. Let's just prevent any backlash. So just always think about non-parametric tests if we're unsure. Okay, descriptive statistics, like I say, the charts are the charts that we just described to you there a minute ago with the length frequency sort of arrangements where we might look at a length and then see how many measurements we've taken at a particular length. It might be weight, it might be age, who knows what we're talking about there. They can be really powerful building blocks, and really sometimes they only need to be there to describe what's going on rather than saying this has to be compared with something else. It might just be the snapshot for that year to show the distribution of what it was like in that particular year or in that particular season. Okay, so to be really reliable while we're in field sampling, our equipment and our data recording equipment should be able to handle extremes in conditions, and they have to have like standard operating procedures and be able to be calibrated quite easily. I mean, we've got some oxygen probes that are so easy to calibrate, it's not funny. pH probes, redox meters, salinity or conductivity meters are sometimes very difficult to calibrate in the field, but trying to purchase one that's really reliable is probably the key to a really solid sampling program. Staff should be briefed in the sampling techniques and aims according to the strategy. Don't send someone out there without an idea of what they're doing. They're just going to go off and do what they want. So really having standard operating procedures that come out of the strategy we talked about before is probably the most beneficial way to go about it. And it may be dot pointed, it might be in a brief package, who knows how it comes out. So when we're recording data, ensure that all data is recorded in an accurate and legible manner. Sometimes they might even be on iPads and the likes these days, where you might have something like an Excel spreadsheet that's pre-populated with drop-down lists, and you just select. You might have your best, most legible handwriter being the person that's acting as the scribe. I'm never the scribe because my handwriting is horrendous, but if I have to, I kind of write slowly. Okay, so summing it up, realistically, for us to understand what we need to do which is most likely a person that might be a team leader in field operations or something like that. We might even just be a field worker. You might just be a fisheries officer that needs to collect random data from a boat ramp. Who knows how you'll end up eventually. But for most of us, you're not likely to be the head scientist that's developing the programs, but it's handy, as I said, for you to know that there is some reasoning behind the way scientists actually develop their programs, more so than them just being a bunch of assholes. So, to be truly reliable, we must just seek to use validated and research methods. Your research scientists would have gone off and developed a program that reflects those, hopefully. Lots of research papers out there related to the types of data they may be wanting to collect. We must be unbiased. We must be able to replicate the process. So it's not like 1 week I go out and do it, and then the following month when I need to go back out there, oh no, we've changed something. That's going to bias your results. It might be an unintended bias, but it's going to bias your results. So we have to be able to replicate it. Recording must be accurate. As I said, handwriting, we might use iPads. Some sort of application these days is no doubt available to be able to download and, to be able to document things. Never assume anything other than inferential assumptions if we're going down the track of parametric testing. So don't assume that someone's picked up the toilet paper. Always make sure that you've got it. Plan for data manipulation as part of the research strategy. So if we think that we're going to have a population where we may need to transform the data to get a really normal distribution, plan for it at the start, because then you don't look like you're cheating. If you go back and you transform it at the end and go, oh, we transformed it to make it look nice, it's kind of biasing your perceived outcome, because you've already looked at the data and then you've already biased it by then saying, hey, but I think it's going to look better if I do that. So already plan for it. Say in your program you might need to do a log transform or a square root transform or a regression analysis as well. So I'm going to leave it there for now, but just very quickly, just think about, I don't want you to perform any of this necessarily. It's more just an indicative introduction to how things may have to roll out if you're part of a sampling program. All right, ciao for now.